What I've done for this lecture is I'm going to break it down into an exocrine and an endocrine pancreas, and then we'll go over the conditions since the pancreas plays two primary roles. So let's break down what the exocrine and the endocrine pancreas do. The exocrine pancreas is what we just talked about. This is where we have our pancreatic enzymes. They get secreted into the duct, and that goes into the duodenum, and then those enzymes can start working. The endocrine pancreas, on the other hand, is where you have hormones secreted directly into the bloodstream to exert an effect. And so we have these things called islets of Langerhans. And in this example, they're secreting a hormone insulin, and it can go straight into the bloodstream. It doesn't have to go into this GI tract right here. So let's talk about the exocrine pancreas and all that entails. I want you to know a few different secretions that the pancreas is responsible for. As you can see here, it's responsible for the secretion of pancreatic enzymes, so we'll talk about that. It also secretes bicarbonate and a combination of water and electrolytes. So I'm going to go over each of these three secretions, and I'm also going to go over especially how these secretions can be modified depending on if you have low flow or high flow. So what we're going to do is we're going to zoom in on one of these ducts. So in these ducts, you have something called an acinus, or a berry, and you have acinar cells that line that. You also have a duct, which, as the name suggests, is lined by ductal cells. And the flow is going to go from this direction. You're going to be secreting stuff in this direction, and it'll flow this way, just to get you an idea. So let's talk about the acinar cells first. These are the cells that secrete pancreatic enzymes. So there you can see some pancreatic enzymes being produced. And they also secrete water and electrolytes. So all of these can be secreted by the acinar cells. Ductal cells, on the other hand, are responsible for secreting bicarb. So there's some bicarbonate going into the lumen. And they can also modify pancreatic fluid. And I'll talk about the process of pancreatic fluid modification after I discuss this. So let's talk about pancreatic enzymes. So these enzymes that we just saw secreted by acinar cells, they get secreted in response to a couple different hormones, namely CCK and acetylcholine. So in our small intestine lecture, we talked about eye cells that end up secreting cholecystokinin. These are cells that are located in our duodenum and jejunum. And then when we eat fatty foods or proteinaceous foods, you're going to get eye cells stimulated. And so once these eye cells are stimulated by fatty acids, let's say, they can secrete cholecystokinin, which has a few effects. But the biggest one you should know is that the gallbladder can contract in the presence of CCK. That'll make this flow down into the through the common bile duct, out the major duodenal papilla, and into the duodenum. But you also get pancreatic secretion and sphincter of Oddi relaxation, which, as we've talked about, if you relax the sphincter of Oddi, you can get more outflow. Another thing it does is decrease gastric emptying, which is a little less important. What I really want to emphasize here is that CCK here, it causes pancreatic secretion, which is kind of what we're seeing in that slide beforehand. All these secretions can be inhibited by somatostatin. That shouldn't be a surprise to you because somatostatin pretty much turns off any hormone or enzyme that you can think of. And so what kind of enzymes do we have in our pancreas, and what do they do? Well, first we have amylase, which is useful for starch digestion. We also have lipases that are useful for fat digestion. And we have several enzymes that are useful for protein digestion. Trypsin, chymotrypsin, elastase, and carboxypeptidase, to name a few. And it's important to note that most of these pancreatic enzymes are actually secreted as zymogens, which are inactive precursors that require activation by another enzyme. So in the stomach lecture, I talked briefly about zymogens, and this is the slide I provided. And you can see here that we have pepsinogen, which you can see right here. And then trypsinogen is what I want to talk about because these are actually this is secreted by pancreatic acinar cells. So trypsinogen is secreted, trypsin, which is the active form, is initially secreted as trypsinogen, which is an inactivated form. So here in the presence of cholecystokinin or acetylcholine, we're going to have pancreatic enzyme secretion, like we just talked about. But these enzymes aren't active yet. So they actually have to travel down to the duodenum. So here they come, and now they're in the duodenum. And once in the duodenum, there's other enzymes, such as enteropeptidase and enterokinase, that can activate trypsinogen into trypsin. And once you have trypsin activated, trypsin can activate a ton of other proteases. So let's just say these are other trypsinogen molecules. This trypsin can turn them on now. It could also turn on procarboxypeptidase into carboxypeptidase and a few other enzymes as well. So some things you should consider with trypsin, well, a few things we need to consider. First off, if you don't have these enzymes right here, enterokinase or enteropeptidase, you can run into some problems because you need these to activate trypsinogen into trypsin. So this might lead to protein malabsorption or failure to thrive because you don't have any activated pancreatic enzymes. In pancreatic insufficiency, you should consider that you don't physically have enough trypsin or trypsinogen in your secreted from your acinar cells. So that could also cause a protein malabsorption or a fat malabsorption. And then in pancreatitis, you almost have the opposite problem where instead of having too few activated enzymes, you actually have too many and they're activated prematurely. And the problem with that is that if your trypsinogen activates to trypsin within your pancreatic lumen without getting into your duodenum, this can really damage your pancreatic ducts and cause a lot of damage to the pancreas itself. So I'll briefly talk about bicarbonate. We've kind of brushed on this before. I just want you to know that the ductal cells are the cells responsible for secreting bicarbonate right here. And how do they do that? So what happens is that S cells can produce a hormone called secretin. And again, we've talked about this. This is a slide from the small intestine lecture as well. S cells are located in the duodenum. And what they'll do is they'll produce secretin, which can increase bicarbonate secretion, which is what we're talking about right here. They also can decrease gastric acid secretions, and they increase sphincter of Oddi relaxation. So it would cause more bicarbonate to flow in. And the whole point of secretin is to basically neutralize all the acid in the stomach. And you can see that each of these three things does that in some ways. Adding more base will neutralize the acid. This will provide less acid anyways. And then this increased sphincter of Oddi kind of helps perpetuate the first one and allows all the bicarb to flow out that outflow tract. So let's talk about water and electrolytes now, as well as pancreatic fluid modification. So as you can see, the acinar cells are responsible for secreting all of these water and electrolytes. And what I want you to remember is that these electrolyte secretions are isotonic to plasma. So what does that mean? If you're isotonic to plasma, that means you have roughly the same concentration of each electrolyte in the pancreatic lumen as you would in the blood. And so here you can see that this would be isotonic, where you'd have a lot more of a concentration of sodium relative to chloride and potassium. So these numbers right here, you'd pretty much see being secreted from your acinar cells. Now, ultimately, when we see, if you measure the electrolyte concentrations more distal in like the main pancreatic duct, for instance, you might not have an isotonic secretion necessarily, and you might not have the same concentration of each electrolyte as you would in this spot. So I want to talk about how ductal cells can actually modify your pancreatic fluid. So let's go over pancreatic fluid modification here. I've just moved this over because I wanted to add a chart here to the right. On the y-axis, we're going to have the concentration of each electrolyte. And here we're going to have the flow rate of the pancreas. So at high flow rates would be in this region, low flow rates would be in this region. So I've added each of the electrolytes as well as water on here. So let's start with an easy one. So water can get secreted, as we've talked about before, by the ACE in our cells, and it'll flow down and it can get reabsorbed. And you don't really need to know too much about water. They don't test about what happens with water in this, but I just know that it can be reabsorbed by ductal cells. Sodium's also kind of boring. Remember from that previous slide about the concentrations, there's a lot more sodium than other ions. And that's why sodium is actually, if you look at our plasma, sodium is the most important osmole in our plasma because there's just so much of it compared to other electrolytes. And what happens here is sodium will flow down, and if it tries to escape, it's not going to be allowed out. So sodium, it's going to start at a high concentration just because there's a lot of sodium in our plasma in general, and it won't get it won't be able to escape here, get excreted. So you're going to have a steady state of sodium. Potassium's the same way. We have less of potassium in our plasma naturally. You know, sodium, if you measure it on like a basic metabolic panel, you'll get numbers like 135 or 140, whereas potassium, you get numbers like 3.5 or 4.5. So you can see there's like a pretty big difference there. And again, if these guys try to escape, they're going to run into the same problem sodium had. So potassium, yeah, it has a lower concentration in general than sodium, and it's just going to stay very steady state. There's no change, no matter how big the flow rate is, even if you're, pushing these potassiums as fast as they can or as slow as they can't escape this. Now we're going to talk about the couple interesting things. So bicarbonate, as we talked about before, bicarbonate is secreted by ductal cells, and it's secreted in the presence of secretin. So S cells will produce secretin that'll act on the pancreatic ductal cells to produce bicarb. And this bicarb, as it flows down here, you can see if it tries to escape, it actually can come back in, okay? So it can get reabsorbed. Now, the amount of bicarb reabsorbed will change depending on your flow rate. So at very low flow rates, if this is all moving very slowly down this way, what's going to happen is that you have more time for bicarb to sneak out. So you can see right there, a lot more bicarb had a chance to sneak out. So at low flow rates, you're going to have a decreased amount of bicarb in the actual lumen. So we'll draw that here. At a low flow rate here, so this is like our low flow rate, you're going to have a low level of bicarb. What happens at high flow rates though? So at high flow rates, everything's moving down this so fast that you don't have too much time for bicarb reabsorption. So you might get one more molecule there. But because of that, because you still have so much bicarb trapped in the lumen here, that tells you that at high flow rates, you're going to have high concentrations of bicarb. And I'll show that one more time. So here at high flow rates here, you can see we're on the high flow rate side. We have a very high concentration of bicarb. And the nice thing about chloride is it's going to do the opposite, and I'll show you why that is. So if bicarb's secreted here, bicarb gets, starts to move distal, and we know bicarb can reabsorb. What's going to happen at low flow is that there's going to be more time for bicarb reabsorption, like we talked about. And why does chlorine have anything to do with this? Well, for every single bicarb that gets out and reabsorbed, you actually have a chloride antiporter that brings chloride into this lumen. So keep in mind, this was at low flow rates where a lot of bicarb can escape and get reabsorbed. You can see that because of that, we actually pumped a lot of chloride back inside this lumen. So at low flow rates, we're going to have very high concentrations of chloride. And vice versa, if you think about the other way, at high flow rates, because there's not that much time for this bicarb to get out, you're not going to have that much chloride that's getting secreted in through this antiporter. So at high flow rates, you can see there's very minimal chloride. And so it's good to have at least seen this mechanism once. You're not going to get tested on the mechanism necessarily. They will ask you about the concentrations from time to time. So a good way to remember that, if you're not able to remember everything, I want you to remember that we've talked about this before a few times now, that the pancreas is great at secreting bicarb. It's a good neutralizer. and you saw how secretin helps in that process. And if you can remember that the pancreas produces bicarb, I hope you'll remember that a high flow rate would produce more bicarb. It's basically if the pancreas is working harder, I want you to just think about that as a more bicarb heavy environment. And then all you have to do is remember that chloride just does the exact opposite. Thanks for watching. I hope you enjoyed the video. Please like, comment, and subscribe for more content.